All right, so I'm very pleased to introduce the final speaker for today, Savita Rani, who's going to tell us about biconservative hypersurfaces in the pseudo-Euclidean space.
Hello everyone, thanks for being here. I would like to thank the organizers for giving me opportunity to present my work here. The title of the talk I am going to present today is Biconservative Hypersurfaces in the Pseudo-Euclidean Spaces, and this is joint work with Professor Ramshankar Gupta, Professor Andreas Arvanitorgios, and Professor Marinas Sata. So these are the contents. First of all, I will give the introduction, then previous works and examples from the literature, motivation, and what is the significance of this study, and then results. So the classification of constant mean curvature hypersurface constitute an important area of research, not only in differential geometry, but in relativity theory as well. Harmonic maps between Riemannian manifolds are critical points of the energy functional given by this, and biharmonic maps are critical points of the bi-energy functional given by this, where tau is the tension field of map phi. So this already explained by Professor Franz and Professor Suboje, and now Els and Sampson did, they generalized this map and they defined the biharmonic map as critical points of the bi-energy functional. And in 1924, Hilbert pointed out that the stress energy tensor associated to a functional E is a conservative symmetric two covariant tensor S at the critical points of E. That is, it is divergence free. So in that case, divergence of stress energy tensor will be equal to 0. And for the bi-energy functional, Jiang defined the stress bi-energy tensors and proved that it satisfies this condition, where tau 2 is the bi-tension field defined by this. So here R tilde is the curvature tensor of target manifold N, and thus if phi is biharmonic, then divergence of S2 will be equal to 0. That is, in that case, stress bi-energy tensor will be divergence free. For biharmonic submanifolds, from the above relation we see that divergence will be 0 only if and only if this tangential part will become 0. So in particular, when we talk about biharmonic, then in that case we take both the conditions 0, that is tangential and normal component both equal to 0. But in case of this biconservative, what we consider only this to be 0, and then this terminology was introduced by Cadio et al. And in this case, the condition of being normal component need not to be 0. It cannot be 0. It can be non-zero also. So in previous works, Hasnis and Blakos studied and classified biconservative submanifolds in four-dimensional Euclidean space and called such biconservative hypersurfaces as H hypersurfaces. Then Turgai obtained a complete classification of H hypersurfaces with three distinct principal curvatures in Euclidean space of arbitrary dimension. Then Gupta and Arvanitorgios examined biconservative hypersurfaces in space forms with four distinct principal curvatures whose second fundamental form has constant no. Later, Fu classified biconservative surfaces in three-dimensional pseudo-Euclidean space or Minkowski 3 space and proved that these are surfaces of constant mean curvature or a surface of revolution or a null scroll. By null scroll, we mean a ruled surface in which base curve and its ruling both are light-like. So in 5, the same author gave classification of biconservative surfaces in de Sitter 3 space and anti-de Sitter 3 space. Later, Gupta and Sharfuddin proved that every biconservative Lorentz hypersurface in n+1 dimensional pseudo-Euclidean space with index 1 with complex eigenvalues has constant mean curvature. And if it is biharmonic, then it is minimal. So what are the examples from the literature? That when we consider of biconservative hypersurfaces in four-dimensional Euclidean space, any hypersurface with constant mean curvature is biconservative hypersurface, and a special family of rotational hypersurface in four-dimensional Euclidean space which have non-constant mean curvature is an example of biconservative hypersurface in four-dimensional Euclidean space. Then the example of this, that product of that de Sitter space with R is in L5 or Minkowski 5 space, where R is greater than 0, it can be representation as this, and in this case vector field will be space-like as the Gauss map. and it has two distinct principal curvatures as K1, K2 and K3 is equal to 1/4 and K4 will be equal to 0. So later, Abhitosh Upadhyay and Turgai gave another hypersurface. They classified in 5-dimensional pseudo-Euclidean space with index 2 the surfaces with 3 distinct principal curvatures, and they also gave the example with 4 distinct principal curvatures, and this is their parameterization. So what is the motivation to study such kind of hypersurfaces? As we know that in harmonic, we talk about minimal hypersurfaces or minimal surfaces. Then we extend our study to biharmonic. Harmonic are submanifolds are subset of biharmonic, and then biharmonic are a subset of biconservative. So it is a wider class to study so that we can obtain the results to study some of the problems that are still open in higher dimension. So what is biharmonic submanifold? A submanifold which satisfies Laplacian of mean curvature vector is equal to 0 is called biharmonic submanifold. Then what is the Chen conjectures gave an open problem that any biharmonic submanifold in Rn+1 with n greater than equal to 3 is minimal. Many authors contributed in this direction. They considered from different point of view. They considered that what are the number of principal curvatures, whether they all will be distinct or some of them will be equal. On that basis, they provide a classification. And however, in higher dimension, it is not available as much. However, recently, Fu, Hong and Zhan settled this conjecture for hypersurface in R6. For when we talk about R6, so we are talking about 6-dimensional Euclidean space. So in that case, many authors studied this conjecture and they settled this in case of Rn+1. Till now, there is no counter example showing that this conjecture is not holding in that case. But then, this conjecture will fail. So one of the point is that when we talk about here, we are talking about n+1 dimensional Euclidean space. But when we go to any Riemannian manifold, and then we talk about biharmonic submanifold in any other Riemannian manifold, then this generalized Chen conjecture fails. There are examples in literature where they shows that this conjecture will not hold true in other Riemannian manifolds other than this Euclidean space. So further, Chen's conjecture is not always true for submanifolds in pseudo-Euclidean space. As I told, in Euclidean space, it is true. Till now, the people studied, the study provides that they are not able to find any counter example in Euclidean spaces. But in case of pseudo-Euclidean space, it is not always true for submanifolds. And in view of this, in 2007, Arvanitorgos, Defer, and Kaymakami gave a conjecture that this is true for hypersurfaces of pseudo-Euclidean spaces. For submanifold, it is not true, but for hypersurfaces, it is true. So one other motivation to study is that the shape operator, when we consider of a Riemannian hypersurface, it is always diagonalizable. But in case of pseudo-Riemannian case, shape operator may or may not be diagonalizable. So it gives us more motivation to study such kind of hypersurfaces in pseudo-Euclidean spaces. So what is the significance of studying such kind of hypersurfaces? They provide a geometric framework for studying higher order elliptic PDEs, and the study of these hypersurfaces helps in understanding the geometry of manifolds and their embedding in higher dimensional spaces. However, these hypersurfaces are related to the concept of conservativity of the stress energy tensor in context of bi-energy. As I mentioned that in biconservative, in harmonic map, we take their critical maps of the Dirichlet energy functional. And when we talk about biharmonic map, they are critical points of the bi-energy function. But in case of biconservative, they are governed by the condition that they satisfy some conservativity law, that is, it is stress energy tensor in this case will be divergence free. And biharmonic hypersurfaces and by extension biconservative hypersurfaces also have application in areas like elasticity and fluid mechanics. As I told that harmonic hypersurfaces are also biharmonic and biharmonic are biconservative, but converse is not true. The biconservative hypersurface is a wider class for studying. So what we considered, we took like 4-dimensional hypersurface isometrically immersed in 5-dimensional semi-Euclidean space, where S can be from 0 to 5 and G is the metric restricted, G bar restricted by this manifold. We denote by xi the unit normal vector to hypersurface with this condition where epsilon can be plus or minus 1 according as our hypersurface is pseudo-Riemannian or Riemannian. Here it is important to know that we are not talking about E4S or something. We are talking about M4S. So it can be any Riemannian manifold or Riemannian hypersurface or pseudo-Riemannian hypersurface. So in this case, the Gauss and Kodaji equations are given by these two equations. So what Gauss equation helps us, it relates the curvature to the second fundamental form. And what this Kodaji equation does, it tells us about the symmetry of the shape operator or symmetry of the covariant derivative of the second fundamental form. Here R is the curvature tensor, A is the shape operator as I mentioned, and it is a linear connection on this hypersurface in 5-dimensional pseudo-Euclidean space. And from this equation we can open it like this. So further, the mean curvature is given by this epsilon h is equal to half of trace of A. When we talk about surface, then we take K1 plus K2 by 2 and take plus minus sign where we want to take their orientation. But here in higher dimension, when we talk about, we take a particular shape operator and define it like this. Now the biharmonic equation can be, because it is a vector equation, it can be decomposed into normal and tangential part. Like when we are in ambient manifold and we come to its hypersurface, then we can divide the tangent bundle to tangent and normal parts. So here what we are doing, we are dividing them in tangent and normal parts. So this is the normal condition above one and this is the tangential part. So what we will say, as I mentioned earlier, that if the tangential part is equal to 0, then what we will consider that our hypersurface is biconservative. So this condition is necessary for hypersurface to be biconservative. This condition is required for biharmonic but not for biconservative hypersurface. So this is a weaker condition than biharmonic, which makes it more difficult to study. So now what we studied biconservative hypersurface with diagonal shape operator in 5-dimensional pseudo-Euclidean space with index S, and we assume that mean curvature is not constant. Although as I told that in pseudo-Riemannian hypersurface case, shape operator can be non-diagonalizable also, but there are different problems in studying that, although many authors studied for some particular index also, but it is not that much easy to study with their non-diagonal. There are some particular form of those shape operators to study when we studied non-diagonal shape operator. So in this case, what we assumed that our shape operator is diagonal. We also assume that mean curvature is not constant. So in that case, grad of h will not be equal to 0. And what it implies that there exists an open connected subset U of hypersurface with grad h at point P not equal to 0 for all points in this subset U. So from the above condition, this condition, that we see that when we put n is equal to 4, then it will become minus 2 epsilon h. And then when we take it from other side, it will become minus 2 epsilon h. So this is the vector, and this is the, like when we talk in linear algebra, then we take ax is equal to lambda x. So in that case, you can recognize this, that here this will be the eigenvalue of this. So from this, we can easily see that grad h is eigenvector of the shape operator with corresponding principal curvature minus 2 epsilon h. So without loss of generality, we assume that our mean curvature vector is non-zero in direction of E1. So therefore, shape operator will take this form, because in that case we are restricting that its first eigenvalue will be minus 2 epsilon h. About others we don't know, so we are taking it as lambda 2, lambda 3 and lambda 4. And the results of this are from this article by Gupta, Arbanito-Gross, me and Sata. So what we are trying to do, we already obtained that our first eigenvalue will be minus 2 epsilon h, and there's some from lambda 2, lambda 3 and lambda 4 will be equal to minus 3 epsilon h, and we can define the grad of h as this equation. So because we consider that our mean curvature vector is non-zero variable, like that is variable in the direction of E1. So it will be non-zero, and in other direction it will be 0. So what we did next, we express covariant derivatives of this orthonormal frame vector fields to equal to this, where epsilon k can take value plus minus 1. These are the connection form, and these are the vector fields from the orthonormal frame. So by using, now what we will try to do, we are expressing the covariant derivatives in this form. We don't know what type of connection forms this will be. So by the known condition that will hold there, we are trying to find these connection forms, find their relation, and trying to check that whether in what condition it will be 0. If we will get 0, then we can reduce our complexity to study the PDEs or equations we will get, or the hypersurface that we want to study. So for that, we, using this compatibility condition, we obtain this condition on connection forms. Further, by putting x is equal to ei and y is equal to ej in the shape operator, that equation I told, del x a y is equal to del x of a y minus a del x of y. By using that equation, we get this equation, and then putting this value in the symmetry, that covariant symmetry of the shape operator, covariant derivative of symmetry of shape operator that I mentioned, that del x a y is equal to del y ax. Using this condition in that, using this in that equation, we will get this equality. So further, by taking that I is not equal to j and j is equal to k, and when all three are not equal, we obtain this equation. These all are things we are doing to find that whether other like eigenvalues will be 0 or non-zero, because we have considered they are 0 in direction of E2, E3, E1, E2, like in direction of E1, other eigenvalues are 0. So what about other directions? So we are trying to find the connection forms and other eigenvalues conditions. So because we have considered that E1 H is non-zero, so but for others it will be 0, because H is like variable in direction of E1 only. So we can say from here that E1 lambda 1 will not be equal to 0, but for other it will be equal to 0. So now what we did, we find a lemma to give some simplification, those covariant derivatives. So what we considered, we took M4 R be a biconservative hypersurface of non-constant mean curvature with all distinct principal curvatures in 5-dimensional pseudo-Euclidean space with index x, S having the shape operator given by this, where I took the a minus 2 epsilon h lambda 2 lambda 3 and lambda 4. Then with respect to suitable orthonormal frame, we got these terms of the covariant derivatives. And what we did to find this, we used the above that these equations that we, relations that we obtained, and then using the condition that this will be equal to 0, or apply this condition to I, j and k, and then we conclude that covariant derivatives will take this form. So for later use, what we claim that our lambda 1 is not equal to any of lambda 2, lambda 3 and lambda 4. And in case if we consider that it is equal to any of the like lambda j, so what we consider that if it will be equal, then what we will get, that even lambda j is 0, and we have said that our lambda j is equal to lambda 1. So in that case, even lambda 1 will become equal to 0, and it will give a contradiction to the condition we assumed in the beginning. So by using this, we consider that they are not equal, and then by using the lemma 2 and the fact of this Lie bracket, we obtain this relation. And when we act this on lambda 1, then we see that even lambda 1 is non-zero, but in other direction, when we apply another covariant derivative, it will turn out to be 0. So then we evaluate Riemann curvature tensor and then take its inner product, and then we find that these type of relations on connection form will hold. So further, now these are the lemmas that we want to use to prove in our main theorem on the biconservative hypersurfaces. So for this, what we did, we assumed that let M be a biconservative hypersurface with constant norm of second fundamental form. We denote by beta the squared norm of its second fundamental form. So from this, we can see that when we take the squared norm, then we take that beta is squared norm. So it will be equal to lambda 1 square plus lambda 2 square plus lambda 3 square and plus lambda 4 square. We keep it separate because we are defined already that it is minus 2 epsilon h, and for others we take summation to find the results. So for simplicity, what we put, we take B2 is equal to epsilon 2 omega 1 2 2, B3 as epsilon 3 omega 1 3 3, and B4 as epsilon 4 omega 1 4 4. So now what we proved by using those conditions, we proved that let M4 be a biconservative hypersurface of non-constant mean curvature with all distinct principal curvatures in 5-dimensional pseudo-Euclidean space with index S, having the shape operator given by the A with respect to suitable orthonormal frame, and let B1 is equal to this. Here B1 is not epsilon 1 omega 1 1 1. We already proved that this omega 1 1 1 is equal to 0. It is just a notation to represent this. So what we proved, that if second fundamental form is constant norm, then we get that these connection forms will be 0. So for this, what we did, we claimed that this is, we first claimed that this is 0. So for this, what we did, first we said that it, suppose it is not 0. Then we, if we use the condition that it is non-zero and discuss two cases, that when B1 is equal to 0 and B1 not equal to 0, in that case we get contradiction to all the distinct principal curvature, that is lambda 1 either come to lambda equal to lambda 2 or lambda 2 will come equal to lambda 3. So in that case we get a contradiction. From that we claimed that this should be 0, and similarly we proved for the other connection forms. So now, in view of previous lemma, what we considered, these conditions we as same we considered. Then we said that if B1 is non-zero, here you see that here we are talking about omega 2 4 4, omega 2 3 3. This type of connection forms we said are 0. But now what we are saying, that in this case, if B1 is non-zero, then this type of that omega 4 2 3, when these are different, they are not same. So then these connection form will be 0 if B1 is non-zero. And if B1 will be equal to 0, then B2, B3 and B4 can be written like this, where alpha and phi are smooth functions and their derivative in direction of E1 is given by this. So further, now we have the main theorem that every biconservative hypersurface in the pseudo-Euclidean space with diagonal shape operator and constant norm of second fundamental form has constant mean curvature. So for this, what we did, this is the idea of the proof. We considered that M4R is a biconservative hypersurface with non-constant mean curvature. Then earlier we just considered that our principal curvatures are distinct. But now we are generalizing some results. So here we will talk about all type of curvatures, that whether two curvatures are, there are two principal curvatures, there are three principal curvatures, or there are four distinct principal curvatures. We can't take one, because we earlier mentioned that lambda will not, one will not be equal to any of lambda 2, lambda 3 and lambda 4. It will be distinct from that. So we can just start from 2, that there can be 2, 3 or 4 distinct principal curvatures. So in first case, when we choose that there are 4 distinct principal curvatures, in first case we took that B1 is non-zero. In that case, we took two subcases, that one, that at least one of principal curvatures is 0, and then subcase A2 in which none of the principal curvatures is 0. So in that case, we find the contradiction to the condition that lambda 1 is non-constant. We considered initially that H is non-constant in the direction of E1, and then later on we said that lambda 1 be not be constant in direction of E1. So even lambda 1 was not equal to 0. But by using these conditions, we obtain that even lambda 1 is 0. So we get a contradiction. So then in next case, we took B1 is equal to 0. And then further we discussed the case of 3 principal curvatures and 2 distinct principal curvatures, and in each of the case we get a contradiction if we consider that this is a biconservative hypersurface with non-constant mean curvature. So means we are implying that in that case mean curvature will be constant, because if we are considering that it is non-constant, then we are getting contradiction. We are not getting that type of result. So in this case, our biconservative hypersurface will have constant mean curvature if we consider square norm of second fundamental form is constant and shape operator is diagonalizable. So these are the references.
Thank you very much. Are there some questions for the speaker?
Thank you. It was very nice. I have a very simple question because I'm not familiar with Lorentz. So you're talking of mean curvature, which is non-constant, you assume non-constant, but then for hypersurface, the mean curvature vector, that's
mean
not
curvature vector. When
the,
we talk
the norm
about, so
is
we are
not the
taking,
mean curvature.
no, when we take squared norm, then it will be some value, no, lambda 1, lambda 2, we are taking the squares of eigenvalues. So we are not talking about that vector. Grad h we are talking about. When we are talking about vector, then we take the condition of grad h.
Okay, so the mean curvature is the sum of the lambda i's, and the other one is the sum of the squares of the lambda
that
i's.
epsilon h is equal to 1 by n trace of that shape operator. So in that form will be.
Thank you very much.
Yeah, go for it.
Biharmonic, right? That's the question. Is it known, for instance, the minimizers, the biharmonic energy, just in simple cases like surfaces in R3?
Yes, it can be, but like when we talk about critical points, we are not talking about that minimizing the bioenergy function, but yes, we can take the condition that it will minimize the bioenergy function.
Yes.
As it minimizes that harmonic map are critical points of energy function, Dirichlet energy functional, then every time they cannot be minimizer. When we talk about the minimizer, then we study the condition of critical points. But every time we cannot take that minimizing condition. So here it depends that what type of property we want to study. If we want to minimize something, then we consider.
Is it known what the minimizer is in certain cases?
No, I don't.
You would assume that, for instance, the Clifford torus minimizes in R3, right?
Yes, maybe like people can find like there can be.
And that you don't know.
Can be minimizer of some energy functional.
I see. Okay.
But in that case, bioenergy functional will be.
Yeah, that's what I mean. Take the bioenergy and minimize, because that's kind of a linear version of the Wilmore problem, right?
Like here,
Wilmore will be Laplacian H.
In case someone is interested in this type of equation, there I used for my purpose that shape operator A grad h is equal to n epsilon by 2h. So those were the tangential, but here these are the equation in that case. So maybe these are also representing biharmonic equation that I represent in mind, that tangential and normal component in terms of shape operator A grad h equal to plus n epsilon h by 2 grad h. So they are representing by this in that case. So this can also be considered in that type of equation, Laplacian and all.
Okay.
Okay, well, if there are no further questions, let's thank the speaker once again.